Next, let us discuss the very important concept in the complex compounds, that is isomerism of in different types of complex. Isomerism in complex compounds. Isomerism. What is isomerism? Let us take the first definition. The complex compounds are having same chemical formulae, The complex compounds are having same chemical formulae, but which exhibit different structures. The complex compounds are having same chemical formulae, but which exhibit different structures are known as isomers. The phenomenon we call it what? Isomerism. The complex compounds are having same chemical formulae, but which exhibit different structures known as isomers. And the phenomenon is known as isomerism. You know, this particular isomerism in complex compounds classified into two types. Let us see how it is classified into two types. What are the different types of isomerisms? In each part. Isomerism classified into two types. One is structural isomerism. Second one is stereoisomerism. Structural isomerism, second one is stereoisomerism. Under structural isomerism, different types are there. What are the types under structural isomerism? Let us see. Ionization isomerism. Ionization isomerism. Hydrate isomerism. Coordination isomerism. Under structural isomerism, ionization isomerism, hydrate isomerism. Next, coordination isomerism. Coordination position. Isomerism. Linkage isomerism. Next one is what? Ligand. Linkage isomerism, ligand isomerism, ionization isomerism, hydrate isomerism, coordination position, linkage, ligand isomerism. Under structural isomerism, these many types are there. Let us see now under stereoisomerism, what are the types? Under stereoisomerism, two types again. This is classified into two types. One is geometrical isomerism. Geometrical isomerism. This also generally we call it as cistrons. Cistrons isomerism. Next one is optical isomerism. So isomerism mainly classified into two types. Under structural isomerism, this many types. Under stereoisomerism, again classified into geometrical isomerism, optical isomerism. This geometrical isomerism we also call it what? Cis-trans isomerism. Under structural isomerism, the different types one by one we will discuss it. Now under structural isomerism, different types are given. Under that, the first type let us discuss now. That is what? Ionization isomerism. Ionization isomerism. See, the complex compound which are having same chemical formulae, the complex compounds are having same chemical formulae, but which produce different types of ions, in aqueous solution. Look here, CO NH3 taken 5 times Br, SO4, and you take CO NH3 taken 5 times SO4 Br. The complex compounds are having same chemical formulae. Say both are having same chemical formulae, and which produce different types of ions put into what are these? Aqueous solid like water you are putting. This cyanide is like this, a complex ion and a sulfate ion. Complex ion and a sulfate ion. See here, same formula, but the formation of ions are different. One you are getting complex, and this is what Br minus. Now this is I am writing complete complex here. CONH3 taken 5 times Br, CO NH3 taken 5 times SO4. Like this, the complex compounds are having same chemical formulae, but which produce different types of ions in aqueous solution, are known as ionization isomers, and the phenomenon is known as ionization isomerism. Now, look here, this isomerism is due to exchange of anionic ligands between the coordination sphere and outer sphere. Observe clearly, this part is coordination sphere, this is what outer sphere. Exchange of ligands between the coordination sphere and outer sphere. The sulfate ligand has come inside, bromide has actually entered into outside the coordinate sphere. Like this, by the exchange of anionic ligands, we are getting this particular isomers. So, the complex compounds are having same chemical formulae, but which produce different types of ions in aqueous solution, are known as ionization isomers, and the phenomenon known as ionization isomerism. Easy to identify. Wherever anionic ligands exchange you are observing, that you can say that those are exhibiting ionization isomerism. Let me give one more point. Number of ionization isomers are equal to number of types of anionic ligands. Number of types of anionic ligands. 2 types of anionic ligands are there in the complex. 2 isomers we are written. Now I will write one more complex in which I will write 3 types of anionic ligands. Look the board. CO, BrCl, NH3 taken 4. I write one more outside the complex, outer sphere I written. 3 different types of ligands are there. The anionic ligands are 3. You can write now 3 isomers. Now, first exchange, second exchange. Look here, CO, Br, NO2 comes inside, and NH3 taken 4 times. Right, this particular complex Cl is outside. Now, one more we can write, one more complex CO. Now, this is Cl you take NO2, NH3 taken 4 times. One side right now the bromide outside. NO2 is outside, Cl is outside, Br is outside. 3 different types of ligands are there. 3 isomers we could able to write. So this is the ionization isomerism. These are all what ionization isomers. Coming to next type, hydrate isomerism. Next one, hydrate isomerism. Now here, the complex compounds are having same chemical formulae, but which are having different number of ions within the coordinate sphere and outer sphere. The number of aqua ligands are differing within the coordinate sphere and outer sphere. Let me show this, how this hydrate isomerism and how hydrate isomers. Take CO, H2O taken 6 I write, hydrate, or you can consider instead of taking CO, let us take, it is better to take chromium. Cr, H2O taken 6, Cl3 is one of the complex. The water molecule and chloride ligands getting exchanged. Look here, Cr, H2O taken 5 times, 1 Cl inside now, and followed by Cl2, 1 water molecule. Next, one more, Cr, H2O taken 4 times, Cl2, Cl, 2H2O. Look here, the complex compounds are having same chemical formula. Chemical formula is same for all this, but which are differing in the number of water molecules within the coordinate sphere and outer sphere. The coordinate sphere, first one is 6, second one is 5, third one is what, 4. The complex compounds are having same chemical formulae, but which differ in the number of aqua ligands, water molecules within the coordinate sphere and outer sphere are known as what? Coordination isomers, and the phenomenon coordination isomerism. Next, this isomerism is due to you are clearly observing the exchange of anionic ligand with aqua ligand. Exchange of anionic ligand with the aqua ligand. And this particular hydrate isomers differ in their physical and chemical properties, that you remember. The 3 complexes are exhibiting 3 different colors, and their chemical properties also different. So this is about hydrate isomerism. Let's come to the next one, coordination isomerism. Coordination isomerism. Coordination isomerism. See, recollect in the nomenclature, we have taken some of the complexes. The complexes containing complex cation and anion, I said. Means, in some of the complexes, there is a complex cation is there, complex anion is there. 2 coordination spheres are there. 2 coordination spheres are there. Let us see how we write this particular 2 coordinate spheres. Look, CO, NH3 taken 6, plus 3, and Cr, Cl taken 6, minus 3. Instead of writing this particular plus 3 and minus 3, we need not write the charge. This is plus 3, that is minus 3, getting cancelled. These are the CO, NH2 taken 6, Cr, Cl taken 6. By the exchange of ligands between these 2 coordinate spheres, you can write one more isomer. Look, now CO, Cr and NH2 taken 6, exchange of ligands completely, this amine ligands, and you can write COCl taken 6, like this. The complex compound which are having 2 neighboring coordination spheres, by the exchange of ligands in between the coordination spheres, one more isomer is produced. Such isomers are known as coordination isomers, and the phenomenon coordination isomerism. Wherever you are getting 2 neighboring coordinate spheres, then you can say that that particular complex exhibit coordination isomerism. Easy to identify this isomerism in comparison to other isomerisms. Next we see coordination position. Coordination position isomerism. Coordination position isomerism. See, this particular complex is exhibited by bridged complex compounds. Wherever the 2 metal atoms are bridged by another ligand, such complexes exhibiting this particular isomerism. So, this isomerism is exhibited by the bridged complex compounds. This isomerism is due to exchange of ligands within the coordinate sphere only. See how I am writing a bridged complex. Look the board. NH3 taken 4 times, let me write this side. This side I am writing NH3 taken twice, Cl2. Sulfate. Yes, British complex. And you are clearly looking on either side, number of ligands are same, but one side is completely amine ligands, other side completely what are 2 amine ligands or 2 chloro ligands are. But you can consider this particular complex. This particular complex we can say unsymmetric. On either side, the number of ligands are same, but type of ligands are not same, unsymmetric. Suppose you want to prepare this particular complex in the laboratory. How you prepare? You are taking cobalt trichloride. You are treating with what? Ammonia gas. Then you are getting 2 complexes. Suppose you are expecting to produce entirely this particular complex, 100% of this particular complex. You are putting the conditions required, temperature, pressure, catalyst, whatever you are using to get this particular 100%. No, 100% of this particular complex can never be produced. Yes, it may be 70% of this complex produced, another 30% of another complex produced. What is this? This is what I said, unsymmetric. Now you see symmetric complex also you are getting CO, then it is OH. On either side, same number of ligands, let us write. Now, same number of ligands, same type of ligands also. NH3 taken twice. NH3 taken twice. Here, one is Cl, the other is also Cl you take. Now, like this, NH3 taken twice, Cl, NH3 taken twice, Cl. How many total ligands? Only 2 to you are written. Is not correct to write. 3 and 3 you write. 3 and 3. So, number of amine ligands are what? How many? Total 6. 3 ligands on either side. How many chloro ligands? 2 chloro ligands. 2 chloro ligands on either side. You can easily understand what is the difference between the first complex and the second complex. In the first complex, you are looking on either side, number of ligands are same, but type of ligands are not same. Therefore, what we call it is what? Let me say it is unsymmetric, not symmetric. Unsymmetric. This one will be definitely symmetric complex. Symmetric, unsymmetric, and symmetric. So, you want to prepare this particular complex only. You want to prepare only unsymmetric? No. 100% unsymmetric we will not get. Along with this particular, definitely 30% of complex you are getting. Next, you want to prepare 100% only symmetric? No, you will not get 100% this one. Definitely 30% you are getting. In the mixture, both will be there. Why this particular both you are getting? The ligands are exchanging within the same coordinate sphere. In the case of coordination isomerism, the ligands are exchanging between the 2 different coordination spheres. But here, the exchange is within the same coordinate sphere. The exchange is positioned. Exchange is localized. Therefore, this particular isomerism, what we are calling coordination position isomerism. Since the exchange is within the same coordinate sphere, the exchange is localized. Therefore, coordination position isomerism. That is coordination isomerism. This is coordination position isomerism. Next, let us see the next type. Let us do now coordination number 5. Now, let me give a complex FeCO taken 5 times. FeCO taken 5 times. Look here, let us follow the same steps. Iron Z is equal to 26. Let us see its electronic configuration. Right, you know well, 3d6 and 4s2. Yes, its oxidation number is 0. Since it is carbonyl complex, its oxidation number is 0. Then electronic configuration remains as such. Then it is 3d6, 4s2. The arrangement of electrons in d orbitals. Let me show how the electrons are arranged here. D orbitals, 6 electrons, 1, 2, 3, 4, 5, 6. The arrangement of electrons in d orbitals. Next, s orbitals. This is the arrangement. Let me write the complex FeCO taken 5 times. FeCO taken 5 times. You know well, CO we have taken as what? A strong field ligand, well known to you, already given the field strength of different ligands. What are strong field ligands? What are weak field ligand? CO is what? Strong field ligand. Then what do we understand by strong field ligand? This particular ligand can push the electrons to pair up. So in this particular complex, definitely the electrons are getting paid. Now let us see how the electrons are getting paid. See this 3d orbital, 4s and 4p. Where the 6 electrons are getting paid? Right, 1, 2, 3, 4, 5, 6. Suppose s electrons are there in the 4s orbital. Let us take like that at the beginning. So once s electrons are like that only, then coordinate number 5, we require 5 orbitals. Yes, 1, 2, 3, 4, 5. But leaving this particular 4s orbitals, the d and p cannot involve in hybridization. Therefore, compulsory s electron has to be shifted to d. Therefore, we are shifting the electrons to d. What? The CO is strong field ligand. Therefore, this particular electron from s orbital shifted to d. Then we have to shift the electron. Otherwise, the hybridization will not take place. The complexation will not take place. Therefore, we are shifting this particular electrons from 4s to 3d. Now, you are clearly looking on the board. The 3d orbital you take, one of the orbital is vacant. We require 5 orbitals for coordinate number 5. Check it, what the hybridization is actually taking place. 1, 2, 3, 4, 5. 5 orbitals. Check the hybridization. You are clearly looking on the board. It is what? D2, sp3 hybridization. D2? No, only D. dsp3 hybridization, only 1d orbital involving dsp3 hybridization. Then you know we already taken in each hybridization what is the geometry. dsp3 hybridization, then it is actually giving rise to a trigonal bipyramid geometry. Trigonal bipyramid geometry. Now let us see what is the information about this particular complex. Information I am writing on the board. Look the board. Information about the complex. Right, we generally take what? First hybridization, geometry, hybridization and geometry, followed by nature of the complex I given, number of unpaired electrons, and you are taking magnetic moment. Let us see what information we are getting for this particular complex. Right, hybridization, dsp3. You are very well solved it. Next up, geometry, trigonal bipyramid, and it is nature of the complex. Consider it is inner orbital complex. Inner orbital complex, you say electrons are getting paid, say low spin, or you can also consider spin paid. Low spin, and also you can take it as what? Spin paid. Inner orbital complex, low spin complex and spin paid complex. Check it, number of electrons, yes, 0. Magnetic moment also coming to be 0. So this particular complex and trigonal bipyramid, this is the information about this particular complex under coordinate number 5. Here we have taken a coronary ligand, that is actually strong field. Once you are taking a weak field ligand in coordinate number 5, what happens? We will discuss it. This is strong field ligand. I will show one more complex with a weak field ligand. Look here, next complex, MnCl taken 5 times, -3. Let us follow all the steps what you are taken for different other complexes. Right, Mn, Z is equal to 25. You know its electronic configuration, 3d5, 4s2. Electronic configuration 3d5, 4s2. Then what is the oxidation number here? +2. For Mn complex, Mn +2. It is 3d5, 4s, 4s0, 3d5, 4s0 +2 oxidation number. I am showing here Free metal ion electronic arrangement. This is the arrangement of electrons in free metal ion. Arrangement of electrons in free metal ion. Let us check the next complex. Look here, Mn Cl taken 5 times. 5 times it is what? Minus 3. Minus 3. MnCl5 taken 5 times. Cl taken 5 times. Minus 3. You know well Cl is what? Weak field ligand. Weak field. Yes, weak field ligand. It is not able to pair up the electrons. The previous case we have taken carbonyl ligand, that is strong field, but Cl is weak field. It is not pushing the electrons to pair up. Electrons remain as such. We have to write all the 5 electrons in the d orbitals. 3d, 4s, 4p. 4p. The 5 d orbitals carrying each orbital single electron d5, but we require 5 ligands and 5 orbitals we require. 5 ligands are there, 5 orbitals we require. Compulsory you have to go for d orbitals also. This I am writing here 4d. 4d. Let's see 5 ligands, 5 orbitals. Come on, take it. 1, 2, 3, 4, 5. So this is the orbitals required. Then it will be sp3d. sp3d the hybridization. The previous case, if you have taken iron pentacarbonyl, that is inner orbital complex dsp3, but here weak field ligand, electrons are not getting paid, so that you are getting sp3d outer orbital complex you are getting. Let us see what is the information we can write for this particular complex. Now it is sp3d hybridization. Geometry, again the same geometry, trigonal bipyramid, and number of nature of the complex, yes, outer orbital complex, say high spin complex, spin free complex. Outer orbital complex, high spin and spin free. Next, number of electrons, you are clearly looking on the board, 5 electrons, and it is what? 5.9 bm is the magnetic moment. This is the information about this particular complex. So we have discussed many complexes, some under coordinate number 6, some under coordinates number 4, some under coordinates number 5. So how the complexation taking place, which are inner, which are outer, we are clearly discussed the many complexes of different coordination numbers. Under the same applications of this particular crystal field theory, the application part, how the hybridization inner and outer we have discussed, what are their magnetic moments and all. Now let us discuss the color properties. How can this particular crystal field theory can explain the color properties of different complexes? Next heading, let us go for color properties. Color properties. Let us discuss what are the important points under this color properties according to crystal field theory. Take the first one. According to crystal field theory, we can thoroughly explain the color properties. We can thoroughly explain the color properties. This can be based on d orbital to d orbital electronic transitions. D orbital to d orbital electronic transitions, or you say it is specifically want to say it is T to the 2 Eg electronic transitions. T to the 2 Eg electronic transitions. T to the 2 Eg electronic transitions. According to this particular concept, you can thoroughly explain D to D transition you say, or T to the 2 Eg electronic transitions. Next, already given there is actually a relationship between absorbed and transmitted color. For example, absorbed, say transmitted, absorbed colors and transmitted colors. Suppose X color is absorbed, Y color is only transmitted. X is absorbed, Y is transmitted. If Y is absorbed, X is only transmitted. For example, blue is absorbed, then orange is transmitted. Consider if orange is absorbed and blue is transmitted. Like this, either you consider XY or blue and orange. These particular pairs of colors are known as complementary colors. Complementary colors. The pairs of complementary colors thoroughly discussed already in D block element. I have given a table which are absorbed colors, which are transmitted colors. What is the relation between these? Clearly explained. The pairs of colors, the absorbed and transmitted, the pairs of colors are known as complementary colors. What is the word? Complementary. These are known as complementary colors. Next, coming to the next point, what are the factors influencing? What are the factors influencing this color properties? That is very important to discuss. These points are already discussed in D block elements, but here it is again important to discuss the same points. Same points I will repeat once again, how the color properties are influenced by different factors. Color properties are influenced by color properties influenced by color properties influenced by 1. Number of unpaired electrons in d orbitals. Number of unpaired electrons in d orbitals or incompletely filled d orbitals. Look here, number of unpaired electrons in d orbitals. Number of unpaired electrons in d orbitals, or you can say number of incompletely filled d orbitals. Number of incompletely filled d orbital. Number of unpaired electrons in d orbitals or number of incompletely filled d orbital. How this? Suppose you consider nickel Cl2 we take and cupric chloride we take. Hence, what is the oxidation number here? Nickel is +2, copper is +2. What is the configuration? D8. It is what? D9. Look here, number of unpaired electrons 2. Here number of unpaired electrons 1. Number of unpaired electrons 2. Number of unpaired electrons 1. Then number of incompletely filled d orbitals 2. Number of incompletely filled d orbitals 1. Both are having different number of unpaired electrons and different number of incompletely filled d orbitals. Therefore, their color never be same. This particular nickel dichloride NaCl2 is having X color and cupric chloride is having Y color. Like this, both are having different number of unpaired electrons, different number of incompletely filled d orbitals. Therefore, definitely their color will be different. NaCl2 and CuCl2, they are having two different colors. So, color property well influenced by the number of unpaired electrons and incompletely filled d orbital. Coming to the second factor, which is influencing nature of the ligands. Second factor, nature of the ligands. Nature of the ligands to see. If we talk about this particular nature of the ligands, look here. I am writing 3 complexes. You can easily understand if the ligand is changing, how the color is changing. Now, I am writing one aqua complex, CuH2O taken 4 times, complex +2. Now, this in this case, the aqua ligand substituted by amine ligand, then you see CuNH3 taken 4 times, right, +2. So, amine ligand I substitute with chloride ligand, check it, CuCl4 -2. One is aqua ligand, one is amine ligand, the other one is what? Chloro ligand. Aqua, amine and chloro ligand. How their color is actually changing? See, first one you remember, it is light blue in color, light blue. This is dark blue in color, dark blue. This is green in color, dark blue and green. As you are changing the ligand, aqua ligand to amine ligand to chloroligand, amine ligand to chloroligand, and the color is changing. So color property dependent on nature of the ligand. Suppose you are substituting this particular chloroligand by another ligand, suppose bromo or iodo, color will be changing. So color property dependent on the nature of the ligand. Next, the third factor I am writing here, see, third factor. It is very much dependent on again geometry. Third factor you can say geometry of the complex. Third factor is what? Geometry. I will give a nickel plus 2 ion, let us take. We have discussed some complexes under nickel plus 2. It is capable of forming tetrahedral complexes, octahedral complexes, square planar complexes. I am writing nickel plus 2, look the board. Now nickel plus 2, it is D8. Nickel plus 2 D8. Nickel plus 2 ion capable of forming complexes with 3 different geometries. Let me see, first one octahedral, I am writing OH, OH stands for octahedral, take it like that. Next square planar complex, and third one let me say tetrahedral. But in all these complexes, look here, nickel plus 2 only, D8 electronic configuration, but 3 geometries are there. The 3 geometries, it is exhibiting what? X color, second one is exhibiting Y color, third one exhibiting Z color. What do you understand by this? In all the 3 complexes, metal ion present is nickel plus 2 and configuration also D8. But what is the difference you are finding? Just geometry differing. But geometry differing, that color is also differing. How can we explain this nature of the ligands and again geometry is influenced the colors? Recollect one point. Here consider first ligand, nature of the ligand. There may be a ligand, a weak field ligand. What I said weak field ligand means? A weak field ligand is causing less splitting as said. Less splitting. When less splitting is there, absorbed color is actually lower energy, greater lambda. Then transmitted color will be different. Once less splitting is there, the absorbed color and transmitted color are differing. The same thing, if strong field ligand is there, splitting is increasing. If based on the nature of the ligand, the splitting may decrease or increase. Once decreasing or increasing, the absorbed color is changing. Once absorbed color change, transmitted color also changing. Therefore, color property dependent on nature of the ligand. Consider geometry. We have taken 3 geometries, clearly given the order of geometries. Square planar geometry splitting is very high, followed by octahedral, followed by tetrahedral. 3 different geometries are there. Yes, nickel plus 2 is there, D8 is there. But based on the geometry, the splitting decreasing or increasing. When splitting is decreasing or increasing, again absorbed color and transmitted colors are changing. So what we can conclude now, based on the nature of the ligand and based on the geometry of the complex, the splitting is decreasing or increasing. Once it is decreasing or increasing, the absorbed color and the transmitted colors are changing. Therefore, color properties are dependent on very much on nature of the ligand and again geometry. This is about explanation. Now I will give 3 different ligands and I will put a table on the board. How this particular different ligands influencing the color property, once again in the form of a table also we can explain. Right. See, I am giving a table here so that you can easily understand ligands. First I am writing aqua ligand, amine ligand, look here, cyano ligand. 3 ligands are written. One is aqua and amine, cyano. Next, field strength. You know, already given a spectrochemical series, clearly given. I said you have to remember entire series also. Then field strength. See, what is the field strength? H2O is weaker ligand than this, weak field, but amine is strong field, but weaker in comparison to Cn minus. The 3 ligands, aqua less than amine, amine less than cyano. This is the order of field strengths. Coming to next one, consider delta O values. Delta O values means, imagine splitting. How they are actually the splitting order of this particular 3 ligands. Yes, delta O of H2O is less than, less splitting because it is weak field. Next, delta of amine less than delta of Cn minus. Okay, this is the order of splittings, this aqua amine and Cn minus. Next, lambda absorbed. Observe this, lambda absorbed. A weak field ligand causing less splitting, no, then less amount of energy required to make a transition between the d orbital. Less amount of energy means longer wavelength. Less energy, longer wavelength. Therefore, lambda of H2O complex is more. Less energy, greater than lambda. Therefore, delta H2O, lambda of H2O, lambda absorbed for H2O complex is less than lambda NH3, less than lambda of Cn minus. This is the order of the wavelengths absorbed. Well known to you again, lambda transmitted, let me give. Lambda transmitted. It is well known to us, a greater lambda, longer wavelength of light is absorbed, shorter wavelength of light is transmitted, and vice versa. Longer is absorbed, shorter is transmitted. If shorter is absorbed, longer is transmitted. That is relation between absorbed and transmitted. So, this particular transmitted you are talking about, lambda transmitted of H2O is less than lambda of NH3 and lambda of Cn minus. This is the order of absorbed and transmitted colors and their wavelengths. How a question appear in the examination? I will give a sample question how the questions are appearing in the examination. I will write a question there. Look here. Which of the following complex? Which of the following complex absorb shorter wavelength of light? Absorb shorter wavelength of light. Shorter lambda of light I am writing to make it shorter wavelength of light. See, A COF6 minus 3, B COH2O complex taken 6 plus 3, C COCl6 you take minus 3. Let me give here D CO NH3 taken 6 plus 3. Question appears like this in the examination. Which of the following complex absorb shorter wavelength of light? Absorb shorter wavelength of light. Then, among these particular ligands, you have to see in which the splitting of orbitals is more. Among these, you have to check it which is the greater field strength. Fluoro and chloro and aqua, these are all weak field. And amine ligand well known to you, it is strong field. Wherever strong field ligand is there, it is causing greater splitting of orbitals. When splitting of orbitals is very high, the electronic transition requiring more amount of energy. More amount of energy means shorter wavelength of light. More amount of energy, shorter wavelength of light. So, option D is the correct here. And the amine ligand is strong field, causing greater splitting, and for electron transition requiring more energy, shorter wavelength. So, answer D is the correct answer, cobalt hexamine complex. Next, let us see the next heading, crystal field stabilization energy. Questions also appearing on this concept, crystal field stabilization energy. I am writing the heading C, crystal field stabilization. Crystal field stabilization energy, CFSC. What is this definition? Let us see. What is crystal field stabilization energy? See octahedral splitting, higher energy level Eg and lower energy level T to the. Let me give 3 electrons. After the splitting of orbitals, electrons are entering into lower energy level. This is now 3 electrons. Next, splitting. This is delta O. It is minus 0.6. Take. It is plus 0.4. Now this is what splitting of d orbitals in octahedral. Let me show splitting of d orbitals in tetrahedral. Then one I am writing on tetrahedral also. How the orbital splitting. T2 E delta T. Arrangement of electrons. In tetrahedral field, the lower energy level is what? Minus 0.6 here. It is minus 0.4. Octahedral it is not 6, it is minus 0.4. Now, what is crystal field stabilization energy? How to define, how to explain this? The stabilization energy gained by the complex. The stabilization energy gained by the complex with the preferential filling of electrons into lower energy levels. Preferential filling of electrons into lower energy levels in octahedral geometry. In octahedral geometry, or the stabilization energy gained by the complex with the preferential filling of electrons into lower energy level, Eg orbitals in tetrahedral geometry. Once the electrons are entering into lower energy level, in the case of octahedral, one electron is entering, then it is stabilized by minus 0.4 times. Second electron is entering, it is stabilized by minus 0.8 times. And third electron is entering, it is stabilized by minus 1.2 times. What are the electrons in the case of octahedral geometry entering into lower energy level T to the orbitals? First electron minus 0.4 times it is stabilized, second electron minus 0.8 times, third electron minus 1.2 times. Similarly, in the case of tetrahedral geometry, one electron preferably entering into lower energy level, one electron entering, first electron stabilized by minus 0.6, second electron minus 1.2, third electron minus 1.8. Like this, when the electrons are entering into lower energy levels, either octahedral or tetrahedral, the complex is getting stabilized. This particular stabilization we call it what? Crystal field stabilization energy. Once again repeating the definition, the stabilization energy gained by the complex by the preferential filling of electrons into lower energy level T to the orbitals in octahedral geometry and lower energy level Eg orbitals in tetrahedral geometry, known as what? Crystal field stabilization energy. Now for this octahedral and tetrahedral, two different equations are there to calculate this particular CFSE. Now let me give you the first equation, octahedral geometry, how to calculate the CFSE values of any given complex. We start from D3, D4, D5, D6, D7, D8 up to D8, weak field and strong field. In both of these particular fields, how this particular CFSE values are changing, how to calculate, we will discuss. You see the calculation part. Octahedral geometry, octahedral, CFSE equation, CFSE, look here, minus 0.4 into, consider T to the electrons, minus 0.4 into T to the electrons, plus 0.6 into Eg electrons, delta O or 10dq, delta O or 10dq. This is the equation for calculation of CFSE for octahedral geometry. CFSE equal to minus 0.4 into T to the electrons plus 0.6 into Eg electron. We will see the calculation for D3, D4, D5, D6, D7, even for D8 we'll see. In both fields, weak field how this and strong field what are the values, we'll check it. Let me take first a weak field. I am writing a W of weak field you take. It is what a strong field. One is strong field, the other one is what a weak field. Now, first you take D3 weak field I am saying, D3 weak field. But one thing, we should know the distribution of electrons. I already given the distribution table, how the electrons are distributed in T2 and EG orbitals in the weak field and strong field already there in the form of a table. But you should remember, you should know how the electrons are getting distributed. Then only you can easily calculate this particular CFSC value. Now, CFSC. For D3 we are talking about distribution of electrons. Now, minus 0.4 into 3 electrons because T2 is carrying 3 electrons in the distribution plus 0.6 into 0, no electron in EG, delta O, or you can take 10 dq. Then it will be minus 1.2 delta O, or you can take it is minus 12 dq. Minus 1.2 delta O or minus 12 dq. This is what a weak field. Coming to the strong field. Recollect again, either in the D3 electronic configuration, the distribution of electrons is identical, even in the strong field and the weak field. When the distribution of electrons is not changing, the value also will not change. Therefore, the strong field and weak field, the D3 system, octal geometry, CFSC value remains same. I will show how again. Now, consider CFSC 0.4, T2 is electrons 3, EG electrons 0.6 into 0, and it is again delta O or 10 dq, delta O or 10 dq. Now, value is coming to be same, minus 1.2 delta O or minus 12 dq consider. So on for D3, the weak field and strong field, distribution of electrons is same and the value is also same. Next let us see D4. D4. Weak field and strong field D4. The distribution you should know. See, T2G3 is coming to be 1. T2G3 is coming to be 1. Now, the value check it. 4 into 3 minus 12 and 6. Therefore, it is minus 0.6 delta O or minus 6 dq. Now, coming to strong field distribution, we check it. T to the 4 instead of 3, it is what? 4. It is 4 electrons in T to the 4. Then the value coming to be 16 minus 1.6 delta O or minus 16 dqs. Next, take 5. D5 electronic configuration, D5. D5 electronic configuration. For D5 electronic configuration, again check the distribution of electrons. No, it is what? 3 and it is 2. 3 and 2. 3 and 2. Look here, 3 into 4, 12 and 2 into 6 also 12. Then the CFSC value for D5 electronic configuration in the weak field case, the value coming to be 0. So, CFSC D5 weak field 0. See, what do you understand by 0 CFSC? Means it is not gaining any stabilization energy. CFSC equal to 0 means the complex is not gaining any stabilization energy. The complex is not stabilized by this particular weak field ligands in D5. Coming to D5 strong field. Then strong field, then this particular 4 electrons becoming 5, then 5 into 4, then the value coming to be minus 2.0 delta O say or minus 20 dq. minus 20 dq or minus 2.0 delta O. Coming to D5, D3, D4, D5, D6, electronic configuration D6. D6 weak field, D6 strong field, both you take. See distribution of electrons. The 1, 2, 3, 4, 5, 6th electron is coming down. Therefore, it is T to G4, T to G4 and EG2. Then it is 16 minus 12, right? 16 minus 12, it is coming to be minus 0.4 delta O, or you say minus 4 dq. Minus 4 dq. Come to the strong field. All the 6 electrons are getting paid in the lower energy level. Check it. It is what? 6 minus 2.4 delta O or minus 24 dq. Minus 2.4 delta O or minus 24 dq. Next, this is what lowest we can say. This is what highest. Lowest means less than minus 4 value is not there. There is no such values like minus 3, minus 3.5, such values are not there. Lowest coming to be only minus 4. Highest coming to be 24 only. Remember, there is no such value like minus 25, minus 26 are not there. Highest, so octal geometry with the D6 configuration, weak field, the stabilization energy gained is lowest. Octal geometry with the D6 strong field ligand, the stabilization energy is what? Highest. That is, highest is minus 24, the lowest is what? Minus 4. Now let us see 2 more configurations are left over. Then let us see D7. D7, I said distribution is important, already given a distribution table to you. Then it is what? 5 and 2. It is coming to be 5, 2, 5, 2. See, 5, 2 means 20 minus 12, the value coming to be minus 0.4, minus 0.8 delta O or minus 8 dq, minus 0.8 delta O or minus 8 dq. Coming to the strong field C, 6, it is becoming 7 electrons now. 7 electron means, yes, it is fully filled, Eg will be 1. Then it is minus 24 and plus 6. So, how much it is? Minus 1.8 delta O you say or minus 18 dqs. This is the value. The last one, check it, D8 electronic configuration. Last one, D8. See D8 electronic configuration, weak field, D8 and strong field. One thing you recollect, I have given in the distribution table, in nickel plus 2 D8, either with weak field you take or with strong field you take. Distribution of electrons will be same. When distribution is same, the value is also same. So let us see how the electrons are distributed. The D8 coming to be T to the 6, T to the 6 Eg2. Then it is the value coming to be minus 1.2 delta O or you say minus 12 dq. See, in the strong field also distribution is same. So it is 6 and 2, 6 and 2. Then the value, what I said many times, whenever the distribution of electrons in T2 and Eg coming to be same, the value, CFSE value also remains same. Therefore, it is minus 1.2 delta O or minus 12 dq. So these are the values, CFSE values. Then how the question appear? Let me show a question in what way on this particular concept CFSE question appears in the examination. See, in which of the following complex, question, which of the following complex having CFSE minus 12 dq. Which is the following complex having CFSE minus 12 dq? A question. See the options now. Cr, NS3 taken 6 plus 2 complex. CO NS3 taken 6 plus 3 complex. Next one, nickel NS3 taken 6 plus 2 complex. Then you take none you take. Okay. Now question appeared like this. Then based on the electronic configuration, based on the distribution of electrons only, you can decide what is the actual value of that particular CFSE value of a particular complex. Come to the first one. Chromium plus 2 it is. No. Therefore, it is what? Chromium plus 2 means D4. It is strong field. Then electrons all are coming to T to the level. The T to the level is what? T to the 4. And T to the energy is what? Minus 0.4. So 4 into 4 it is coming to be 16. Therefore, this is not our answer. Coming to the next one, cobalt. Cobalt plus 3. Cobalt plus 3 means D6. Cobalt plus 3 means D6. D6, amine ligand, is strong field ligand. All the 6 electrons getting paired in the lower energy level. See all the 6 electrons coming and pairing in the lower energy levels. This is what 6. 6 into 4 coming to be minus 24. Right, it is not our answer. It is coming to be minus 16. It is coming to be minus 24. But let us see this nickel. Nickel plus 2 means you know well D8. D8 made electronic distribution. You see D8 I am writing electron distribution. How in T2 and easy orbitals. Now 1, 2, 3, 4th electron, 5th electron, 6th electron, 7th electron and 8th electron. This is the distribution of electrons in this particular T2Z. How many electrons are there in the here? 6. 6 into minus 4, it is what? Minus 24. It is 2 electrons, easy. 2 into 6, 12. So minus 24 plus 12. Then minus 12 is the answer. This is the correct answer for this particular complex. Question appears like this in the examination on CFSE values. Let us see what are the defects in crystal field theory. Different aspects and concepts I clearly explained, and possible questions, how the questions are appearing in the entrance exam is also given. You see later on and some more questions also. But what are the defects you find in this particular crystal field theory? Defects in CFT. Defects in CFT. Now one. According to the first postulate, you check it. He said metal to ligand bond is purely electrostatic force, highly ionic, no overlapping of orbitals, no transfer of electrons, he said. No overlapping of orbitals, no transfer of electrons. 100% are highly ionic, is said. The bond is electrostatic force, highly ionic, is said. Highly ionic. Therefore, this theory fails to explain covalent characters of complexes. Covalent characters. Covalent characters are different. Covalent characters of different complexes. This cannot thoroughly explain because he says ionic and highly ionic. Often it may be 100% ionic. Therefore, covalent properties of metal complexes cannot be explained by this particular theory. Next, he said no overlapping of orbitals is said between the metal and ligand. Without overlapping of orbitals, we cannot explain the pi bonding. This theory fails to explain pi bonding in metal complexes. As he said, no overlapping of orbital. Therefore, this cannot explain pi bonding in metal complexes. Coming to the third, and this theory explains color properties according to D to D electronic transitions. Based on d orbital to d orbital electronic transitions only, we can explain the color properties in CFT. But that means what you understand? There should be at least one unpaired electron in the d orbital. At least one. No unpaired electron, no color. But you see, some of the complexes, some of the compounds you see KMNO4 and K2CR2O7. KMnO4 and K2Cr2O7, check it. Mn is here +1, well known to you. Chromium is what? +6, well known to you. In both of these, Mn +1 means D0, chromium +6 means what? D0. Even though D0 configuration, D0 electronic configuration, but they exhibit color. You might be seen this particular KMnO4 and K2Cr2O7 in the laboratory itself. Now, KMnO4 is dark purple in color, K2Cr2O7 orange in color. But what is actually D0 electronic configuration there? They should not exhibit color, but exhibiting color. This is due to very important phenomenon known as charge transfer phenomenon. This is very, very important to remember. Charge transfer phenomenon. KMnO4 and K2Cr2O7, even though D0 configuration, exhibit color due to charge transfer phenomenon. But crystal field theory fails to explain the color properties according to charge transfer. CFT cannot explain the color properties according to charge transfer. Next, this theory is giving the order of field strength of the ligands, we agree. The field strength is much more dependent on basicity of the ligand. Greater the basicity, generally it is possessing greater field strength. Greater the basicity, you can understand greater will be the field strength. But if you consider the increasing order of field strength in the spectrochemical series, increasing order of field strength of ligands in the spectrochemical series, OH is, suppose you consider OH minus and H2O you take. Yes, OH is more basic. OH field strength should be greater than water. But actual order what he has given, OH minus is having lower field strength than H2O. Like this, there are some deviations. There are some deviations in the increasing order of field strength. The correct order is not followed here and there in the spectrochemical series. There are some deviations in the increasing order of field strength of the ligand. Such concept is also not thoroughly explained by crystal field theory. So first, what we said, this covalent characters cannot be thoroughly explained. Second one, what we said is no overlapping of orbitals. By this we cannot explain the pi bonding. And color properties, yes, thoroughly explained, but point is that only D to D transition is said. But some of the complexes exhibiting color according to the charge transfer phenomenon. The color properties based on charge transfer cannot be explained. Coming to the next, there are some deviations in the increasing order of field strengths. Such concept OH minus is actually given as lower field strength than H2O. This is not the correct order. There are some deviations. The increasing order of field strength of the ligand, this particular concept also not thoroughly explained by CFT. This is about CFT, postulates, applications, different coordination numbers and color properties, CFS values, and some important the defects in crystal field theory.